Welcome back, everybody. In this video we're going to take a look at the updated PIC 18F4550 USB demo board. You might recall from the previous USB demo board video that we took a look at the finished firmware and host software, but we didn't actually go through the process to create either. And also the USB code for both the firmware and host software wasn't really separated out in terms of the USB functionality versus the rest of the program, which might have made it difficult to reuse the USB functions in a future project. Also, for a first demonstration of USB communication with the 18F4550, the circuit board really was unnecessarily complicated. It had some unnecessary parts on there. So in this video we're going to take a look at an updated version of the 18F4550 USB demo board, and here's some of the differences. The circuit board is going to contain only the bare minimum parts to demonstrate USB communication from both host to device and device to host. Hopefully that more simplified presentation will make it easier for you to make your own project as you follow along. And then also for both the firmware and host software, we're going to make both of the projects from scratch. We're going to import USB function libraries, which are much more modular, to separate out the USB functionality from the rest of the program. And then we're going to write the main program for each of them step by step. These changes should make it much easier for you to make your own project if you're new to USB communication, or if you're new to USB communication with the 18F4550. So I wholeheartedly encourage you to follow along and make your own. Let's get started. Okay, so to get started today, we're going to go to www.18f4550.com, and please bear in mind my page here is under construction at the moment. Eventually I'm going to make this all much nicer, but we're definitely going to look for the link. This might move in the future, but I'll try and at least keep it more or less on the main page. We're going to look for the link updated 18F4550 USB demo board, and that brings us to the updated USB demo board video page. And once this video is done, I'll put the video down here, but for the moment here's what we're looking for, is this USB files.zip download, and this is going to contain 5 files. It's going to contain USB demo board updated 1920 by 1080. This is going to be the circuit diagram that we're going to use today, and then that's also going to contain 3 firmware files for us, USB functions.c, USB functions.h, and USB functions.linker. C and H, of course, are the C and H files with the USB functions in them. .linker is a special linker file to allow the PIC 18F4550 to perform HID USB communication. And then for the host software, we're going to download, also in the zip file, we're going to download USB class.cs, which is a C# class containing host software functions for performing USB HID communication. So let's go ahead and save the download. Alrighty, so after saving the zip file to the directory of your choice, let's go ahead and extract all. And we can extract to the same directory as the zip's been saved to. And let's go ahead and take a look at our circuit diagram. So let's take a quick tour. We'll start with pin 1 and then go counterclockwise. So pin 1, of course, goes over to the programming header. And then we have 2 switches here on RA1 and RA2. And then we have the usual power and ground for the chip on both sides. And then 20 megahertz oscillator on pins 13 and 14, and of course the 18F4550 internal phase lock loop will amp this frequency up to 48 megahertz. And then we have our two 22 picofarad caps to match. Then we have our USB cap on pin 18, and then on the other side we have our USB connector on pins 22 and 23. And then we have 3 LEDs to demonstrate output from the chip, and then our programming header, and that's it. So next, let's Alrighty, so here's our breadboarded circuit, again starting with pin 1 and then rotating counterclockwise. We have our 2 switches, and then our clock and our 2 capacitors to match the clock, and then our USB capacitor. Then moving over to the right side of the chip, we have the USB connector, and then our 3 LEDs, and then the programming header at the top. If you're new to breadboarding circuits, please see the previous videos on the 18F4550 for more on that. And now let's get on to writing our firmware. Alrighty, so before we start writing our firmware in MPLAB, let's first create 2 new directories here in our download folder. So we're going to call them USB demo board firmware and USB demo board host software. And next, let's move USB functions.c.h and the linker file into firmware. And then we'll move USB class.c into host software. And now let's go ahead and fire up MPLab. And once MPLab comes up, we're going to go to Project, Project Wizard, Next, and Device 18F4550. And our preferred compiler is going to be Microchip C18. And now we're going to create our new project file. So we're going to make sure that we save that in USB demo board firmware, the folder that we just made. And we'll name it USB demo board. And that's the correct path, and then next, and then finish. And now we're going to go to File, Add New File to Project, and again making sure that we're in the USB demo board firmware directory. We're going to make a new file, usbdemoboard.c, and save. And let's go ahead and put a comment in at the top of that indicating the name, usbdemoboard.c. And then we're going to go to Project, Add Files to Project, and again make sure that we navigate to the correct directory, USB demo board firmware, and then files of type, set this to all so we can see everything, and then we're going to add .c, .h, and .linker to our project. And there's the 4 files that we're going to have for our project today. Bear with me for a moment here while I do some resizing. Alrighty, so now we've got all 4 of our files open, USB functions.linker, .h, .c, and USB demo board. So let's take a quick look at each of the 3 files that have been pre-done for us. So USB functions.linker, this is a linker file that is specifically made to allow HID communication to be performed with the 18F4550. This file is entirely credit to Microchip. It's directly out of their firmware stack examples for USB communication. We don't need to get into the details of all these addresses here, but essentially this is a combination of what the compiler needs to work with and also what the internal hardware is in the 18F4550, and then also what the standards for USB HID communication require some special addresses here. But we don't have to worry about all the details. We can simply include this linker file in our project, and then MPLab will use this linker file by default rather than the linker file that ships with the C18 compiler, and then HID communication will work well for us. So next, let's take a quick look at USB functions.h. At the top of USB functions.h, what I've done for about the first 300 lines here is kind of provided a cut and paste template for you to paste into your main program. So we're going to cut and paste this section here into USB demo board.c shortly to get us started. But for the moment, if we scroll down, note it says begin cut and paste here. For the moment, if we scroll down a little past line 300, there's end cut and paste. Then we get to at this point, this is actually truly the beginning of the .h file. So what we're going to have in here is we're going to have a number of pound defines and type def structures to provide for USB communication. So here we have the USB communication states going from detached to configured, and so on. The device descriptor, pound defines, and there's the device descriptor structure, and so on. All the things that are part of the USB spec as far as implementing USB HID communication. At the very end, we're going to find our function prototypes. Let's take a quick look at USB functions.c. So here we're going to start off with our global variables. There's quite a few of them. Fortunately, we're only going to need to see some of those in USB demo board.c, and we'll get to that in a moment. And of course, here we have our device descriptors. Note that those are specifically put in ROM. And again, that's part of the USB spec. And then we have a number of functions. We have USB init, which is called once. It will be called once from USB demo board.c to perform the USB initialization functions, and then USB tasks will be called repeatedly by USB demo board.c to perform the routine USB transfers to keep the connection established. And then we have the other functions that those 2 functions call. And again, this file is relatively lengthy, but once we get down to the end, we're going to have the functions that we're going to call from USB demo board.c. And here they are. We have transfer from host to device via endpoint 1, and transfer from device to host via endpoint 1. And then to simplify the parameters of these, we've included two wrapper functions here, receive via USB and send via USB, that take no parameters. And these are the functions that we're going to call from usbdemoboard.c. So now we're going to return to usbfunctions.h, and just a little bit after line 300, where we see here end cut and paste. So we're going to start here and highlight up to where we find begin cut and paste, and go ahead and Control X to cut that, and then we can delete the begin cut and cut and paste notations there. And now let's paste that into usbdemoboard.c, and at this point we can test that we should get a clean compile. And there we are, we have a clean compile. So now at this point we're ready to customize usbdemoboard.c for our particular project. Okay, so before we actually start writing any of our own code, let's take a quick look at the template that we're provided here. So we start with our includes, 18F4550.h and usbfunctions.h. Then we have our chip configuration settings. These are a straight copy-paste from the internal and external clock blink video. Please see the prior tutorial on that if you're unclear on any of the chip config settings. And then we're going to move on to our pound defines. Due to the specific hardware of the 18F4550 and the linker file that we're using today, it's necessary to remap the high interrupt vector address and low interrupt vector address if we were using interrupts. We're not going to be using interrupts today, but that's okay. We can just leave the functions there, and they're going to be there in our template if we'd like to use those in a future program. And then next, let's take a look at our global variables. So these are three variables that you'll notice the extern keyword here. These are actually declared in usbfunctions.c, but we're going to need to see these three variables in our main file here, hence the reason that we're using the extern keyword. And these variables are USB device state, so that starts with the USB device unconnected and steps all the way through the various USB states through to a fully configured device state. And then we're going to have two buffers from host to device buffer, which is a 65-byte array, but we can't use the first byte of that for data as part of the USB spec. We have to leave that as 0, which it's initialized to in usbfunctions.c. And then also from device to host buffer is the same size, and byte is simply a renamed unsigned character here. And of course it should be pretty clear from the name which direction the data goes from host to device buffer, so that would be input from the perspective of the chip, and then from device to host buffer that would be output from the perspective of the chip. Of course it would be the opposite if you're thinking in terms of the host perspective. And then we have these nice comment blocks, so as you decide which of these bytes 1 through 64 that you have to work with, as you decide what the purpose of each of those is, then you can change the comment here and put in your description for what that byte is going to do in your program. And we'll come back to that a little bit later. And we have another comment block for the second buffer. And now let's take a look at our function prototypes. So in this case, usually we would have two function prototypes for the high interrupt vector and then two for the low interrupt vector. In this case we need three because of that special linker file. So we're going to start with high ISR. Let's take the high priority interrupt to start with, for example. So high ISR, that's going to be at interrupt vector 8. And again, that's part of the 18F4550 hardware, that the high priority interrupt has to be at address 8. And then that's going to have this assembly statement that's going to jump to remapped high interrupt vector address, which is going to jump down here. And then that's going to have one assembly statement in it that's going to jump to your high priority ISR code, which is here. So again, in this program we're not going to do interrupts, but if you were going to do interrupts, you would put your actual high priority interrupt code here. And then these two previous functions, you could just leave those exactly as they are, and as long as we're using that special linker file, everything will end up working out correctly, and it will get to your interrupt code here. And then essentially we're going to repeat the same process for the low interrupt vector, which is again, internal to the 18F4550 is always at hardware address 18. Then we have our remap low interrupt vector address, which is going to jump to your low priority ISR code, and then you would put your actual low priority code here. And then in case a reset occurs on the chip, we have the remapped reset vector at address 1000, and that's going to simply go to startup. So let's get back to the rest of our function prototypes after the interrupts. And that's only going to be two, or we're going to have your init, so that's where we're going to init all the things that are particular to our board. So that's, in our case, that's going to be the 2 switches and the 3 LEDs today. And then we're going to have your tasks, so that's going to be the function that's going to be repetitively called to perform the tasks pertaining to our board. So let's go ahead and take a look at main, which is going to be after our interrupt function. So main is relatively simple here. We're going to call USB init, again, that's in USB functions.c, and then we're going to call our init, or your init rather, to stick to the literal wording, and that's going to be in this file, and we're going to write that here. And then this endless while loop is going to call USB tasks, and of course that's also in USB functions.c, and then we're going to call your tasks, which is in this file. And your tasks is already kind of started for us here, and we're going to go ahead and finish that in a moment. Okay, so we'll come back down to the end of USB demoboard.c momentarily, and we'll write your init and your tasks. But first, let's jump back up to the pound define section, and we're going to put in a few defines to rename our pins, and also our states for our 2 buffer variables. So first, let's rename our input pins, and of course those are going to be the 2 switches. And now we're going to rename our output pins, so that's going to be our 3 LEDs. And let's go ahead and reference our circuit diagram here. So our 2 switches are on RA1 and RA2, and then our 3 LEDs are going to be on RB1, 2, and 3. Alrighty, so now we can introduce some pound defines to rename our LED states. And also our switch states, so we don't have to throw in hard-coded numbers when we're using from host to device and from device to host buffers. Okay, so before we jump back down to the end of the program and start writing the functions, let's update our comment table here for the host to device and device to host buffers. Now, this is such a relatively simple demonstration program, this doesn't really matter, but if you were using all 64 available bytes in both buffers or anywhere near, it would be very helpful to update this comment table to keep track of which bytes stood for which things in your program. So here's how we would do that. And then we're going to scroll down to from device to host buffer. So now we're ready to jump back down to your init and write some statements to initialize the pins on our board. So as we'll note from the comments here, your init, the intent here would be an initialization code specific to your board. So for example, tris registers, adcon registers, setting up interrupts and timers if you were using that, etc. So for our board first, let's set all the AN pins to digital input-output. That way we can be sure that our switch inputs will be read as digital inputs, and therefore the 18F4550 will be able to read our switch inputs correctly. So next we're going to configure our input pins with the tris registers. And now we're going to configure our output pins on the tris B register. And our last remaining task in your init is going to be to initialize our 3 LEDs to 0. And now your init is complete, and we're ready to move on to your tasks. So let's take a quick look at the comments provided here. So the G underscore USB device state global variable. That denotes the current state of the USB connection. So that steps through these 6 states here, starting with detached and ending up in configured. So the idea is before we actually do anything with the USB information, we definitely want to make sure that USB device state equals configured state. And then we have our 2 buffer arrays to work with, from host to device buffer and from device to host buffer. And once we've set our arrays, or we need to read from them, we're going to call the functions receive USB or send USB as applicable. And we already have a skeleton written for us here. So if USB device state is configured, then we're going to receive via USB. Then we're going to process our inputs, and then we're going to set our outputs. So let's clarify what we mean by inputs and outputs here. When we're saying inputs, we mean, for example, a command from the host to the device to turn the LEDs on the circuit board. That would be an input from the perspective of the chip, which is how we're writing the firmware. So let's go ahead and write our 3 input conditional statements here. So we're going to have if G underscore from host to device buffer 1, because again, remember we can't use 0, we have to start at 1. So if that's equal to LED 1 on, then we're going to turn LED 1 on. And again, this is where it's nice to have our pound defines to rename our numbers for us, so we can simply say LED 1 on and LED 1. Else, if from host to device buffer equals LED 1 off, then we're going to turn LED 1 off. And in case we need this statement to debug, we'll put else should never get here. And now we're simply going to copy and paste that statement for LEDs 2 and 3 and make the applicable changes. Now we're ready to move on to our outputs. So what outputs in this context is going to mean is going to be that we're going to have the switches on the board. So the microcontroller is going to read the switch states, and then it's going to send an output via USB to the host, and then the host on the host software is going to display what the switch states are. So that way we'll have demonstrated USB communication both from the host to the device and from the device to the host. So here's how that's going to look. So if switch equals 0, so remember the switches, as a necessity of the way we have them wired on the board, they're logic low. So that's if switch 1 is on, remember that's logic low, then we're going to have the statement G underscore from device to host buffer 1 is going to be assigned switch 1 on. Else if switch, whoops, that should have said switch 1 there. So else if switch 2, or if switch 1 rather was still on here, equals 1, so that's going to be else if switch 1 is off. Again, remember logic low. Then we're going to say G underscore from device to host buffer is going to be assigned switch 1 off. And once again, if we ever have a concern with these statements, it can be helpful to put an else statement, and then we can put a debug, turn a debug light on at this point if it's necessary. But ideally it should never get here. And we only have two switches on our board, switch 1 and 2, so now we can simply copy and paste this statement from switch 1 for switch 2. Alrighty, so now we're done writing our firmware, and we can go ahead and save and compile and keep our fingers crossed. And there we go, build succeeded, and so our firmware is done, and now we're ready to move on to our host software. Alrighty, so now our firmware is all set, and now we can start on our host software. So let's go ahead and fire up C#, and when C# comes up, we're going to go to File, New Project, and we're going to name, make sure you have Windows Forms application selected, and then we're going to name our project USB Demo Board, and then OK. And when that comes up, the first thing we're going to do is save it, and we're going to browse and verify that we're saving it to the USB Demo Board host software directory we had made earlier. Select folder, definitely uncheck create directory for solution, and then choose save. And let's go ahead and save and back out of C# for just a few moments here. So if we look in USB Demo Board host software, we're going to find that here's the USB class.cs file we moved in here earlier after the download, and then C# created this directory for us here, USB Demo Board, and then put the actual files for the project within here, but we don't need that extra layer of directory. So we're simply going to Control-X, cut all these files out, and we're going to paste those into our USB Demo Board host software directory. So now this extra directory here, USB Demo Board, is empty. So we're going to go ahead and delete that. And there we go. So now we have all our files pertaining to the project in one directory. So of course all these are the files that C# created for us, except for USB class.c, which we moved in here after the download. So let's go back into USB Demo Board solution, and then we're going to go to, well, first we have to choose our project, then go to Project, Add Existing Item, and again verify we're back to the USB Demo Board host software directory, and then we're going to bring in USB class.cs. And that's now going to appear on the tree in the left. And let's go ahead and take a look at that. So the first thing that we're going to note in USB class.cs is these two notes at the top here. So one, to get a successful compile, because we have to use a mix of managed and unmanaged code to perform our USB hardware related functionality, we're going to have a function later on in the program here. Let's skip to the very end for just a moment. This function read file managed buffer. It's necessary to use the unsafe keyword with this function to be able to successfully read via USB. So to accommodate that, we're going to need to go to project, the project name, and then properties, and then build, and then check allow unsafe code. So let's go ahead and do that. Project, USB Demo Board properties, build, and then we're going to check allow unsafe code and save. And now we can exit out of that. And now the second thing to note is that we're going to change the name of the namespace to match our project. So here where we have put your namespace here, we're going to change that to USB Demo Board. And before we actually get back to the form designer and start designing our form and then form 1 and write our code, let's take a quick look at USB class. So we have some constants here: connection successful, connection not successful, and then a number of particulars here that are necessary to accommodate USB HID communication. And a lot of this file, actually the majority of it really, is from the Microchip USB firmware stack example. So this is mostly credit to Microchip. I've renamed some of the variables though and rearranged things a little bit to make it a little bit more readable. So here we have the import of the DLL functions that we're going to use to perform the USB functionality: set up device interface class devs, set up device interface, enumerate device interfaces, and so on. And then we have our member variable section. We have the device ID. We've left this as the default in the USB firmware stack examples, which is also what it is in our firmware, so that's okay. But if you ever need to change it, this is a public variable. You can simply assign a new string to it in the format shown. And then we're going to have our connection state variable. And then just as in the firmware, we have two 65-byte arrays, we can't use the first byte, but the name is essentially the same as in the firmware, from device to host buffer and from host to device buffer, and those are public, so we'll be able to read those from our form 1 code. Then we have some other global variables, and then moving on here we have the constructor, where we initialize from host to device buffer and device to host buffer element 0 to 0, and again those can't be changed, we have to work with elements 1 through 64. And then we have the attempt USB connection function. We're going to call that from our form 1 code, and that's a pretty lengthy function. There's quite a bit to do to establish USB communication. And then down here we have read file manage buffer, which takes a number of parameters, and then we have two wrapper functions that we're going to call from our form 1 code: receive via USB and send via USB. And these are wrapper functions so that no parameters are necessary to pass in, and those functions call read file manage buffer and write file. So now let's go ahead and take a look at our form designer. Alrighty, so now we're ready to start putting some components on our form. Go ahead and do a quick resizing here. Bring up properties and toolbox. So we're going to add 4 labels. And then we're going to add 3 group boxes. And to avoid squinting, let's go ahead and highlight all these and then change the font size to 12. And then before we go any further, let's go ahead and name all our labels and group boxes. So the first label is going to be LBL info. And the second label is going to be LBL switch states. And then we're going to have label switch 1 and label switch 2. And then our group boxes are going to be named GB LED 1, GB LED 2, and GB LED 3. And now we're going to go ahead and add 2 radio buttons to each group box. Scroll down until we get to radio button. And next let's go ahead and name our radio buttons, and then everything will be named. So we're going to name these. These are going to be pretty consistent across the 3 group boxes. So for the first group box, it's going to be RDO, LED 1 on, and then of course this will be RDO, LED 1 off, and then we're going to have RDO LED 2 on, and RDO LED 2 off, and then of course RDO LED 3 on, and RDO LED 3 off. So we have one more control to add to our form. Actually, it doesn't go directly on the form, but we're going to double click on timer, and that's going to go down here, and then we're going to name that TMR USB. And then we're going to set the interval property to 50. Now that's 50 milliseconds, so in other words 20 times per second this timer's tick event is going to be called. And then we're going to set the lower of each of the radio buttons to be checked by default. So that's going to be checked true, checked true, and checked true. So at this point all our components have been put on the form and named, so I'm going to go ahead and fast forward here during moving around some of the components and setting the text on them. Alrighty, so now that our form's been all resized and we have all our text filled in, everything's looking nice for us, we're going to go ahead and double click on the form, and that's going to write Form 1 Load for us. Then we're going to double click on the info label at the top, and that's going to write Label Info Click for us. And then we're going to double click on the timer event here at the bottom, or the timer control rather I should say, and that's going to start to write the tick event for us. And in addition to the code that the C# environment has started for us, we're going to add a constant section and a member variable section. Actually, we're only going to have one member variable. And then we're going to add one more function in addition to what the environment started for us. After label info click, we're going to add the function attempt USB connection front end. And again, we'll come back and write that later. And let's go ahead and neaten up our code a bit. Alrighty, now we're ready to start writing our code. Let's start with our constants. So we're going to introduce, just as we did in the firmware with our pound define statements, we're going to have some constants for the LED command states and the LED switch states. Alrighty, now we're ready to move on to our member variable, and we're only going to need one of those, and that's going to be USB class, and we'll call it USB object. And then in the form 1 constructor, we're going to instantiate that. So that's going to be USB object is assigned new USB class. Now we're ready to write form 1 load, and that's going to be only one line. And we're simply going to call attempt USB connection front end. And that's all we need for form 1 load. Now we can write label info click, and this is going to be one simple if statement here. So we're going to do if USB object dot connection state equals USB class dot connection not successful. Then we're going to call attempt USB connection front end again. So the idea here is, and then we'll end the if statement. So we're going to verify when the label is first clicked on, we're going to verify that we're not already connected. And then we're going to attempt to connect again. So let's take a look at this function here again for a moment. So when the user first starts the program up, if the USB connection isn't there, say for example the user forgot to connect the USB cable, or maybe the USB cable wore out and went bad, the info label, we're going to have it display as red, and it's going to note that the connection was not successful. And then it's going to indicate to click the info label again to attempt a second connection. So in other words, if the info label is clicked, if we're already connected, then we can just exit the event. But if the connection hasn't been successful yet, then we should attempt to connect again. So now we're going to write the attempt USB connection front-end function that's actually going to attempt the connection and then update the label either green or red depending on how successful the connection was. So just in case the program should get stuck at this point, which almost never happens, but just in case it does, we'll do label info.text is assigned connecting. And then we're going to attempt the connection. So here's how we're going to do that. USB object dot connection state is going to be assigned the result of USB object dot attempt USB connection. Okay, so now we're going to have two conditions for here for if that connection is successful or not. So if USB object dot connection state equals USB class dot connection successful, then we're going to update label info background color to be system.drawing.color.lime green. And lime green looks better than it sounds. It's actually a nice green color that will indicate to the user that there was not a concern. And then we'll update the label info text to say connection successful. And then we're going to turn on the timer. Else if USB object connection state equals USB class connection not successful, then we're going to update the info label background color to be system.drawing.color.red to indicate a concern. And then we'll update the label info text to be connection not successful. Click here to retry. And that's going to end USB connection front end. And now we're ready to write USB timer underscore tick, which is where we're actually going to handle our inputs and outputs. So we're going to start timer tick off by calling USB object dot receive via USB. So that's going to get the packet from the chip. And then we're going to have some if statements here pertaining to our switches. And then we're going to update the form based on what the chip relayed to us as far as the switch states. So that's going to be if USB object dot from device to host buffer 1 equals switch 1 on. Then we're going to update label switch1.text to say switch 1 is pressed. Else, if USB object dot from device to host buffer 1 equals switch 1 off, then we'll update label switch 1 text to indicate switch 1 is not pressed. And then for switch 2, we're pretty much going to copy and paste the code from switch 1 and change all the switch 1 references to switch 2. Alrighty, now we're ready to write the code for our radio buttons, and what those are going to do is that's going to command the 3 LEDs, LED 1, 2, and 3, on the circuit board to either turn on or turn off. So we'll have if RDO LED 1 on dot checked, if that equals true, then we're going to do USB object dot from host to device buffer 1 is going to be assigned LED 1 on, else if RDO LED 1 off checked, if that equals true, then we're going to do USB object from host to device buffer one is going to be assigned the command LED 1 off. And just as with the switch statements, or switch handling code I should say, up here, now we're going to simply repeat this same statement for the radio buttons for LED 2 and 3. Alrighty, there we go. So now the only remaining thing to do is call USB object dot send via USB, and that's going to conclude our timer function, and that's going to end the class and the namespace. So now let's go ahead and save our program and cross our fingers while we compile. And there we go, rebuild when all succeeded. So let's go ahead and load our program and give it a test. Alrighty, so we have our firmware and host software compiles complete, and our PIC-Kit 2 is connected to our breadboard. So let's go ahead and fire up the PIC-Kit 2 software. And there we go. PIC-Kit 2 found and connected, PIC device found. So now let's go to File, Import Hex, and we'll navigate to the hex file that we compiled earlier. And there we go, USB demo board.hex. And let's go ahead and write that. And programming is successful, so now we're going to go ahead and disconnect the PIC-Kit 2. And we're going to go ahead and connect the other end of our USB cable to our USB connector on our board. And there's the dedoink, so our 18F4550 is successfully recognized by Windows as a USB device. So now we can go ahead and fire up our our host software rather. And I'll go ahead and zoom in. And there you can see the connection is successful. Just to test our error handling, let's go ahead and X out of that. If we just disconnect our connection now and start up our host software again, sure enough, there we get connection not successful. Click here to retry. Reconnect, there we go, dedoink. And if we click here to retry, now the connection is successful. So now we can go ahead and test our switch functions. So switch 1 is pressed, switch 1 is not pressed. There we go, that's working. Same with switch 2. And now let's go ahead and test our LED functions. That lower LED there is that's only to indicate power. These are the actual 3 LEDs here that are going to indicate the LED state as we're commanding them. So there's LED 1 on, LED 2 on, LED 3 on, LED 1 off, LED 2 off, and LED 3 off. So there we go. We've performed both input and output via USB with the 18F4550. So this project is a definite thumbs up. Congratulations! You now know how to make your own USB demo board and write firmware and host software to perform USB communication with the PIC 18F4550. In upcoming videos, first we'll take a look at the motor controller project again, but this time with USB communication, and we'll write the host software in C# to control the motors. Then after that, we'll redo Tracker from the OpenCV tutorial series, but with a pan and tilt platform controlled by 2 servos, enabling the webcam to move to track objects. See everybody.